All right, so let's go ahead and get started. I've asked you to verify your WebAssign logins, so hopefully you guys have done that or will do that shortly. And then other than that, I'm going to post homework number 1 very shortly, so people look out for that definitely before the next lecture. I'll post that. So we talked about electric charge before. So charge is the thing we use to bookkeep the electrical force. So protons and electrons have this interaction. We just try to bookkeep that. Q is the variable we use for charge. The proton and electron have the same amount of charge, the elementary charge. It's just one is of one kind, which we call plus, the other is minus kind. That means that anything that has an equal number of protons and electrons adds up mathematically to 0, which we call neutral. We can also choose to express the charge not in terms of elementary charge, but in terms of coulombs. So coulombs is the SI unit for charge. And one elementary charge is 1.6 times 10 to the minus 19th coulombs. So protons and electrons have equal and opposite charge. They, don't forget though, they're not copies in every other way. The masses are definitely very different. Okay. So what we have here is that opposites attract. So protons, electrons, one being plus, one being minus, those attract, whereas like charges repel. So protons are proton, and electron, electron. So here's what we're up to. We've gotten to the property of the object that we need to be concerned with, charge. And having charge means you belong to a club where you interact with other charges. So the property of the object itself is Q, and the interaction it has with other objects because of this is the electric force. So that's what we're getting into today, the details of the electric force. Okay? So if you have Q, you belong to a club where you attract or repel other Qs, and that's called the electrical force is that interaction. It's very much the same as in gravity, where the intrinsic property of the object is called mass. And if you have mass, you belong to the club of attracting other masses, and those interactions are dealt with the force of gravity. The main difference, of course, is that gravity is always attractive. That's the only thing that can happen in gravity, and so we only need one kind of mass. Mass is always positive. Whereas in the electrical force, you have to be able to account for both attraction and repulsion. There are two different kinds of things. There's plus charge and minus charge. And the reason for that is because having two different kinds of charge, plus and minus, is what allows us to account for two different things, attraction and repulsion. So what we're going to do today, to start off, is write down the force law. This is called, I guess we can call it the electric force law. And this, of course, gets a name. It's called Coulomb's law. It's the same person who got the unit of the electrical, SI unit of electrical charge named after them. Also has this law named after him. And I'm going to, in kind of talking about electric and gravitational force already kind of in parallel, I'm going to put down for you the gravity force law. So we can compare and contrast. This is called, if you remember from Physics 1, Newton's law of universal gravitation. So this is something that hopefully you remember, or at least it'll ring a bell once I write it down. And this is two important forces to compare because, as I mentioned, these are really the two fundamental forces we've introduced in the class so far. All the other forces, as I mentioned in the last lecture, besides gravity, are really just special cases of the electrical force. The electrical force is what's responsible for atomic and molecular cohesion, which is ultimately where normal force, tension, spring force, buoyancy, those things all come from. So, electric force law. If we have two things that have electrical charge, they will experience some kind of interaction with each other, just like on the gravitational side, if there's an intrinsic property of mass that each one has, they will experience some kind of interaction. And what we're concerned about in this interaction is what's the size of it and what is the direction. So I'll write those down. And we can start with the direction part since we already kind of mentioned it. Gravity is attractive. That's kind of all there is to the story. If you're a mass, you attract other masses. But in the electric force side, it depends on if it's a charge like yourself or it's a charge that's the opposite. If you're a light charge, you repel from other light charges. If you're opposite, then you attract. Opposites attract. Okay? So that part, that's all set. Let's fill in the size. Let's start with gravity because this should be review. The amount of gravitational attraction that will be experienced between two objects, well, first of all, depends on their masses. If one or both masses are larger, they'll be attracted to each other more. So if you have more mass, you belong more, or you're a more fervent member of your club of attracting other masses. The distance also matters. So the force is not constant. It depends on how far apart you are. The force gets weaker with distance. Okay? So this is a particular type of proportionality. For those of you, hopefully, if you didn't take Physics 1 with me, you talked about this important skill. So the force of gravity is proportional to the inverse, meaning denominator, of the square of the separation. So this is known as an inverse square law. Okay? Inverse square law. Okay? So what does that mean? Well, you can do a lot with this. You can certainly say that at the most basic level, if R increases, right, you take them further apart, what happens to the force? Does it increase or decrease? Decreases. The force of gravity gets weaker when you take the two things further apart, all things else being equal. If you don't change the masses or anything like that, you simply take them further apart. But with proportionalities, you can go to the next level. We can say, not only are we going to increase R, let's say increase R by 3 times, triple it. By what factor will the force of gravity be reduced? 1/9. It'll be 1/9 of its previous value, right? So if you don't see how I did that, I'm going to guess that you didn't take Physics 1 with me and you didn't learn this skill. So if you feel like you need some catching up, let's talk about it outside of class. But I know that the people who took Physics 1 with me, I really tried to harp on this skill because it's an important skill. Okay? So basically, whatever factor you affect R by, the force of gravity will be affected by 1 over that factor squared, because that's the relationship they have in the equation. And of course, the final piece of the formula is the universal gravitational constant. And that is basically the tuning constant which nature gives us. Because we, of course, are using for mass and radius and for force, we're using certain units, and there's going to have to be some kind of adjustment, right? Because if you put 1 kilogram and 1 kilogram 1 meter apart, the force of attraction is not 1 Newton. It's way too big. So the purpose of this is to actually tune this into what nature tells us, with the universal gravitational constant being 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. So as a reminder, that makes sure that if you take a 1 kilogram mass and another 1 kilogram mass and you put them 1 meter apart, it makes sure that the force is actually in agreement with nature, which the force is 6.67 times 10 to the minus 11th newtons. Very minute attraction. The ugly clump of units on the end of that universal gravitational constant is, of course, just to make sure that all the units work out very nicely. So that's a review of the gravity force law. Hopefully this is familiar. One thing I do want to remind you, and this is just as a friendly reminder, I'm not sure if you even need to do this, but R, if you have that these have finite size, R you should measure center to center. Okay, so that's a big thing, right? If you're trying to find the gravitational attraction between the Earth and the Moon or something like that, measure center to center. Okay. Are there any questions on that gravity law before I move on to the electric force law? Okay. So the reason I mentioned the gravity law is that the electric force law is very similar looking. Okay? If you want to find the size of the electric force law, or the size of the electric force, oh, and I guess I should probably draw in the forces. How about that? So here's an attraction. So I should draw in the force of attraction. It's equal and opposite, right? Newton's third law. So they pull on each other with an equal and opposite, equal force, opposite in direction. The size of that force is given by the equation. I have to be a little careful, of course. I can't commit to saying if it's an attraction or repulsion on the electrical side until I say what are the charges. So I guess let's just, for the sake of drawing, we'll make this one plus and this one minus. So then I can also draw that as an attraction. Like that. Of course, if there were like charges, I'd have to draw them repelling instead. But either way, what I'm interested in at this point is the size of the force, okay? I'll figure out on my own if they attract or repel, but I just want to know the number. How many newtons of force do they exert on each other? And for those of you that might not be used to this notation, whenever I write a force, but the vector hat is left off, that means I just want the size of it, okay? So this is just going to be a size. It's plus, by definition. If you have a vector quantity, it can't have a negative size. Maybe some of you that have taken physics elsewhere, maybe you see it like this, okay? This is the size of the force. I just prefer to save myself some writing, okay? So that means size of a force. Okay, so let's write down the law. Well, the law, it's again going to depend on how much the objects have the property that makes them a member of this club. So just like if one or both objects had more mass, they had more gravitational force. If one or both objects have more charge, they will participate more in the electrical force. The size of that force is not constant, varies with distance, and in fact, it's exactly the same variation. It's also inverse square law. The force gets weaker when you take the charges further apart, and it does so in the exact same manner as gravity. Okay? So you can say things like if you quadruple the R, then the force will get cut by how much? It'll be 1/16 of its previous value, right? So things like that. The only difference in the two equations is that just like nature provides a number here to kind of make all our units work out, there's another number called Coulomb's constant, K, which is going to be basically telling us something about the strength of the electrical interaction that we happen to have. Okay? Let me tell you what that value is. Getting a little crowded here, so let me not have to work inside these boxes anymore. K is called Coulomb's constant. It's the analogous quantity to the capital G, the gravitational constant, and its value is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Now this is rounded off. It's not exactly this, but this is kind of our official value for the class. So don't use a different round off because there might be some error in WebAssign that might result. Notice that the units have this, the units of this is kind of ugly, but it's basically the same as the units of this, except the kilograms, which is mass, has been replaced by the units of charge, right? So hopefully not surprising. And then the number certainly seems larger. 9 times 10 to the 9th is way bigger than 6.67 times 10 to the minus 11. But it's a little bit of a false comparison because 1 kilogram and 1 coulomb are, of course, completely apples and oranges. So you can't really make any inferences from that. So we're going to have to get our hands dirty with a calculation to really get a sense of comparing these two force laws. So that's one of the next orders of business. We'll kind of try to do some kind of comparison of how strong or weak these two forces are in a typical situation. Question?
When we're making calculations with Coulomb's constant, do you want us to carry that significant figure down or kind of pretend that it's an exact number?
Oh, so a word about significant figures generally for my class, I don't care. Okay, so that's, you can do that in chemistry or whatever, but for me, we do error analysis in lab. In lecture, you can basically assume, use all the values that all the decimal places that you're given, put them through, avoid round off. Generally, when you're plugging stuff into WebAssign, if you include at least 3 significant figures, it's not going to ding you for round off. If you start rounding off more than that, you might go outside the tolerance of what WebAssign accepts. So what I would say is keep everything, then put in at least 3 significant figures into WebAssign. If you put more, it won't penalize you. But if you put less, it starts to be rounded off enough that it might think you made an error when you actually didn't. So that's a general approach to stuff in lecture. Are there any other questions? Okay, so I guess the only other thing I want to add here is there's a unique problem to this law that this law doesn't have. Now, here masses are always positive, so we're going to get a size regardless. We're going to get a positive number, but here, if we have a plus charge and a minus charge, that might actually make this negative, and we don't want that because we just want an amount of newtons. We're going to deal with the direction completely separately. And so for that reason, I would recommend that you absolute value the charges. If one of them, therefore, is negative, it avoids you having a negative simply because the only purpose you're trying to get this law, the only thing that you're trying to get this law to do is output a number, how many newtons. You're going to worry about the direction separately, and it's going to be a vector anyway, so plus and minus is not going to be adequate. When you have 2 dimensions and higher, vectors there's a lot more to the direction than that. So, so we'll get to that probably later today when we start basically combining these two things, right? Both the size and direction makes the entire force, right? So we'll do some review there. It's going to be largely review of Physics 1. How do you do vector addition of forces, things like that. Before I do that, though, and kind of get more into the nuts and bolts examples, let me do a quick problem or example where I take a typical situation. It's going to be a hydrogen atom, and I'm going to get a sense of how relevant are each of these two forces in that situation. So I'm going to compute in a typical atomic situation what's up with gravity, what's up with the electrical force, and kind of get a sense of, on the atomic scale, what's important and what's not important. Have any questions before I do that? Okay, so let's do an example. So I'll call it example 1. And just to give you a sense of what is important about the example, we're going to do a comparison of the electrical force and gravitational force in this situation. So let's go ahead and draw our hydrogen atom, which is simply a proton and an electron. So we're going to assume our relatively simplistic model here, where the electron is orbiting like a little planet around the proton. Why does the electron go around the proton instead of vice versa? It's simply because of the masses, right? Right? The proton is much more massive. It's like, why does the Earth go around the sun and not vice versa? It's because the Earth is way more massive, okay? It would be technically correct to say that they actually do orbit around a mutual center of mass, but that mutual center of mass is basically pulled way over to the proton side because it's more massive, okay? So, what do I want to do? Let me give you a sense of the typical distance between these two. The typical distance is, I'm going to say, is about 10 to the minus 10th meters. Okay? Now, of course, it depends exactly on where the electron is. You may know from chemistry that there's a ground state and excited states, and the electron is slightly different places, but that's about typical. Okay? Let me put approximately here just so that you don't think that that's always what it is, but that's what we call the order of magnitude. Okay? It's around 10 to the minus 10th meters, not 10 to the minus 5th or 12 meters or something crazy like that, right? This gives us a rough idea. In fact, 10 to the minus 10th meters even gets its own name. It's called an angstrom. It's an A with a dot on top. If you're wondering if that's some weird vector symbol, it's not. It's just a Swedish A, because Angstrom's was Swedish, so his name is spelled with an A with a dot on it. So that's a typical non-SI unit for length at this scale. Okay. So the proton and electron, they will attract each other for two reasons, right? They both have mass, so the fact that they both have mass means that gravitationally they attract each other, right? All masses attract each other. And they will also attract each other because they're opposite charges, right? One is a plus and one's a minus, so that's another reason why they would be attracted to each other. So I can draw that in. Electrical force, electrical force. So it's true that both of these forces might, let's play devil's advocate here, both of these forces might play a role in keeping this atom together, okay? And of course, if you were going back to physics 1, both the electrical force and the gravitational force, which are the actual forces, may play a role in the necessary force to hold something in a circle, right? If this thing is moving, it wants to fly in a straight line, and it requires some force to bend that turn and keep it around the proton. In fact, we have a name for the amount of force that's required to hold something in a circle. Centripetal force, right? So the actual forces that act provide the required force. Does anyone happen to remember what the formula is for centripetal force? mv squared over r, okay? By the way, you'll find a section on your exam equation sheet which is like the old hat stuff, right? Here's the things that you might need from physics 1, okay? And there's at least one problem, if not more, on your homework number 1 where you do need to reference some things you may have forgotten. I'm not expecting you to have memorized them. Anything you might need from physics 1 is available to you on the equation sheet. So here's my goal in this question. I'm not going to do much with this. I can't spoil all the fun for your homework. But I do want to look at the relative strengths of the electric and gravitational force. I want to get a sense of, are they of equal partnership? Maybe one does more of provides more of the centripetal force than the other. Let's find out. So let's use our equations here. So let me clear some space. First, let's find the gravitational attraction. So we're going to have to put in the mass of the proton, mass of the electron, and then their separation. And that'll give us the gravitational attraction that they have to each other. So we have all these values. The universal gravitational constant, so that's a universal constant, so you throw that in. The mass of the proton and the mass of the electron I gave you last time. The beauty is if you have a proton or you have an electron, you don't have to wonder what its mass or charge is. Those things are always the same. So I gave those to you last time. They're on the equation sheet as well. There's a constants corner where you can find all those kind of things. The only thing I really needed to supply you is how far apart they are, and of course I did that. So I will leave it to you to plug in all that stuff. And the exact number should come out to be, I think it's 8.9 times 10 to the minus 30th newtons. Seems like a small force, but we're also down at the atomic level, so it's hard to get an intuition. How big or how not big is that for an atom? Of course, the ultimate thing we're going to do is compare it with the other force, the electrical force, and then we're going to get a sense of how much bigger is it. I'll show you another really useful trick. If you just want to get a general sense of how big an answer is, you can just put in things with just the power of 10. So if you just want to get a very broad sense of what something is, sometimes instead of equals I'll put squiggle. That means sort of approximately-ish, okay? So I'll put in the gravitational constant is 10 to the minus 11. Not going to worry about the rest of it. The mass of the proton is 1.67 times 10 to the minus 27, so let me just put in the power of 10. Mass of an electron is 9.11 times 10 to the minus 31, so 10 to the minus 31. And then this is 10 to the minus 10 meters squared. So this you can just collect the powers of 10 and let's see what we get. We get 10 to the minus 11, minus 27, minus 31, and then 10 to the minus 10 squared is 10 to the minus 20th, right? And then I flip that up, so I add 20. So let's see, what does that add up to? Does that add up to, I don't have it written down. What does that add up to? Someone have good at arithmetic in their head? What is that? What is it?
Negative 49.
Negative 49? Really? Oh, wait. That's not even close to what we got. Is it? Did I write it down wrong? See, this is why we check, right? Apparently there's something that really went off. You got 49, negative 49? Oh, yeah, so I copied down the wrong number. Oh, good. So that thing I gave you earlier is not right. So that's what we checked. So I believe the number should come out to be 1.01 times 10 to the minus 47. It's not quite what we got, but if we want to just have a wide ballpark, that's right, okay? Of course, the reason why they're not quite right is because I chopped big parts of those numbers. But if I want to get a general sense, it's sometimes very useful. And you'll see that in this case, when I get the next part, whether it's 10 to the minus 47 or 10 to the minus 49, which by the way is a factor of 100 different, you think, how could that be close enough? It's going to turn out to be close enough. Okay? So this is just kind of a nice trick when you want to just get a very, very broad sense of where a number falls. Okay? So the next order of business now is to compute the electrical force and compare it. So now I'm going to compute the electrical force of attraction. So I have K times the charge of 1. Well, the mass of or the charge rather of a proton is plus E. The charge of a electron is minus E. So they are equal and opposite charges, and then of course I divide by R squared. That's Ke squared over R squared. That'll be the electrical force of attraction. And again, I could estimate how big this is. Let's do that. Just as an estimate, K is 10 to the 9. Remember that Coulomb's constant, now even though I'm not putting in the units here, let me remind you that that is the Coulomb's constant SI units, so I can't leave it as E. I have to put the charge in coulombs. So that's 10 to the minus 19 squared divided by 10 to the minus 10 squared. So let's figure it out. That would be 10 to the 9. I have minus 19 times 2 is, what, 38? 9 minus 38 plus 20. Okay, so 29 minus 38, negative 9. So, way different than what we got before, right? Way different. It's clear already, just from a very, very coarse estimate, that the electrical force is way, way bigger. Okay? In fact, the exact number is 2.3 times 10 to the minus 8. It's just a little bit bigger because, of course, of these other numerical factors. It's 10 to the minus 8, which is 10 times bigger than our rough estimate. Okay? So, if we wanted to make a comparison of the relative importance of gravity and electric force and keeping it on together, let's take these numbers. Let's at least use the right power of 10. So 10 to the minus 47 and 10 to the minus 8. One of the ways you can get a sense of how relatively important they are is by taking a ratio. So let's take a ratio. That ratio, let's do it as electric force over gravitational force. So if we say get 100 for that, it means that the electric force is 100 times more, right? If we get 1,000, it's 1,000 times more. Let's see what we get. So the ratio will be approximately, well, this was around 10 to the minus 47th newtons, 10 to the minus 8th newtons, and that ratio is 10 to the 39, I believe. Yes, 40 minus 47 plus 8. Okay. So the electric force is not 100 times bigger, not 1,000 times bigger, not 1,000,000 times bigger, not 1,000,000,000 times bigger, not 1,000,000,000,000 times bigger. It's a 1 followed by 39 zeros bigger. Okay? So the big takeaway here is that the gravity doesn't even matter. Okay? In fact, this is practically, for all intents and purposes, 0 in comparison. By far the most dominant factor in atomic cohesion is the electrical force. The gravity force plays essentially no role whatsoever, okay? Sometimes in physics when we want to make a point, we might say something like this. The electrical force is much, much greater than the gravitational force in this case. So that when you really want to make your point that it's not just greater, but much, much greater, you put the symbol twice, okay? So, the electric force is the big show. In fact, if you want to completely ignore the gravitational force, you incur almost no errors. It just doesn't matter, okay? It's like a mosquito and an elephant, okay? So the electrical force is the only thing that matters. That's on an atomic scale. Gravity doesn't matter. Now, you might say, well, let's do something to give gravity a chance, okay? It basically is irrelevant for holding together a hydrogen atom. So I'm going to try to do something to even the score a little bit. So what I'm going to do, I'm going to somehow magically imagine that this proton can stay stationary, but that this electron can choose to either orbit around it because of its electrical attraction, or I'm going to put the entire Earth here, and I'm going to see if the entire Earth can gravitationally pull hard enough on the electron to steal it away, okay? So this is a second gravitational force that I'm going to calculate, not between the electron and proton, but its competition is the electron and the Earth. I'm going to see if the electron is pulled hard enough by gravity by the entire Earth so that it might fall away from this proton it's attracted to. So let's calculate that. So I'm going to compute a second gravitational force between the electron and the entire Earth. This should be bigger, right? So we got a gravitational force. Wait, did I take this ratio backwards? Yes, I did. The bigger number should have been on the top. Sorry about that. 10 to the 8th minus 8 newtons was gravity, and much smaller gravitational force is 10 to the minus 39. Sorry, 10 to the minus 47, right? Is that right?
Yes.
Okay. All right. So I'm going to see my gravitational force between these two, electron and proton before, was 10 to the minus 47th. I'm going to find a larger gravitational force now. Obviously, the electron is going to be pulled harder by the Earth because it's much more massive. So let's find that out. So now it's the mass of the entire Earth times the mass of the electron over the distance between them squared. What R should I use? Any ideas? Should I use 10 to the minus 10? No. You have to remember, how do you measure that R? Center to center. So I have to measure from the electron all the way to the center of the Earth. That's assuming that, of course, the electron is relatively near the surface, but we then measure center to center, its entire radius of the Earth. So we got to put that in there. Radius of the entire Earth squared. Now, before you worry, oh, do you need to know the mass of the Earth and the radius of the Earth? Well, you don't, because this stuff generally gets prepackaged for you. What is that?
9.8 meters per second.
9.8 meters per second squared. That's our normal shortcut for how we compute a gravitational force, right? We just take the mass and we multiply it by 9.8. So we take our gravitational force. Let's just estimate. So it's 10 to the minus 31 kilograms. G is 9.8, but let's just round it off to 10. So we get 10 to the minus 30th newtons. Is that bigger than before? Yeah, it's way bigger than before. It used to be between the proton and electron, it's 10 to the minus 47. Now it's 10 to the minus 30th, which is substantially larger. No surprise, right? The entire Earth has a larger pull on electron than one single proton. But I want to point out, even still, this is insignificant, okay? 10 to the minus 30th is still way smaller than 10 to the minus 8th. So what my point is that the electrical force is so significant on an atomic scale that a single proton pulls harder on an electron than the entire Earth can gravitationally pull on that electron. Okay? Now, if you need evidence for this to be the case, you are not a pile of loose protons, electrons on the floor, right? Despite the pull of gravity from the Earth. You are able to easily maintain atomic cohesion because the electrical forces that are holding your atoms and your molecules and so forth together, they could care less. Gravity is not significant to them. Okay? So on an atomic level, gravity is basically irrelevant. Okay? So the entire Earth pulls on an electron gravitationally way less than a proton pulls on it electrically. So you may sometimes hear that gravity is considered a fairly weak force. Now that's a hard argument to make when you say, well, it seems pretty strong to me. But let me point out that number one, you are not a pile of loose protons, electrons on the floor. And number two, whenever you fall, when you hit a solid surface, you stop. Why is that? Well, the reason why is that the outer layer of electrons in your shoes are repelled by the outer layer of electrons in the floor. So you have the electrical force to thank for not having you go through the floor. Okay? So if you want to imagine it, when you have two surfaces that don't want to chemically interact, that's a different story. Basically, the Coulomb force is what stops you from going through there. In fact, we call the manifestation of that the normal force. Okay? There's also, if the two surfaces are kind of like this, they're rough, and two surfaces are like that, there may be a component parallel to the surface. So if you take a look, for instance, at these two electrons and they're repelling, it repels like this. They repel directly. And for instance, we could break that force into two components. We could break it up into a component that's perpendicular to the surface and one that's parallel to the surface. The one that is perpendicular to the surface, we sometimes call it a normal force. And what do we call the one that's parallel to the surface? Friction. So two forces that we kind of learned in Physics 1, they're really just manifestations of the electric force. It also brings up an interesting implication of what it means to touch something. When you touch something, what are you really doing? Are you really clinking electrons with it? Are the electrons rubbing against each other? No. If you look at the equation, or any inverse square law, as the distance approaches 0, the force approaches infinity, right? So in order to have two electrons literally go into each other, you would need an infinite amount of force. It's not possible. So when you touch something, it's really bringing the electrons as close to each other as you're strong enough to do. So what is the nature of touching? The nature of touching is just to bring your electrons close to something as you possibly can, but you can't actually bring them to actual physical contact. When you're touching something, there's always empty space between. Okay? It's just so small that you, of course, can't see it with the naked eye, but you can't really ever truly touch something on the atomic scale. Are there any questions on that? Okay, so this hopefully gives you kind of the lay of the land in terms of on the atomic level, gravity is really important, or sorry, electrical force is really important. So if I've successfully convinced you how insignificant gravity is, I have to kind of bring you back a little bit and say, well, how does gravity ever end up mattering of anything, right? It seems so important in our daily lives, right? So the reason why gravity seems significant to us is because we live in a very special case where gravity even has a chance, okay? So that's the next thing I want to address. So if on an atomic scale, the electrical force is so large that gravity practically doesn't matter, how is gravity so important for us on the, I guess I'll call it the everyday scale? So what you have to do is really stack the cards against the electrical force and for gravity before they have hope of being equally significant, okay? Or both important. And here's how you do that. Remember that if you want gravity to be bigger, you need a lot of mass, right? More mass means more gravitational interaction. Well, what's mass made out of? Protons, electrons. So if you want to have more mass, right, like you have more mass than a hydrogen atom because you have way more protons, electrons. But coming with that may potentially be more charge, right? So what you have to do is very carefully build up a huge collection of protons, electrons to get all that mass. You let gravity get bigger, but you also have to have those protons, electrons build up in essentially equal numbers so you're still neutral, okay? So what you need to do is have a very large collection of protons and electrons. That's what you are, okay? So you have a very large collection of protons and electrons, which means that you start to have a large amount of mass, but of essentially equal number, equal amounts. So your charge, your net charge, is still approximately 0. That's how you end up giving gravity a chance. You have very, very large collections of protons, electrons, where gravity can take hold and get to be significant. By the way, of course, you don't notice the gravitational attraction between you and your friend. When I say large collection, I mean like really large, like an entire planet's worth to be able to pull down on you. But have it essentially be equal amounts so that there's no charge buildup. Okay? So, for instance, you're attracted to the Earth in a very significant way because you're both very, very large collections of mass of essentially equal amounts of charge, right? So that's why you notice the force of gravity. It's because you have this extremely skewed situation, right? You do everything you can to help gravity get bigger and everything you can to keep the electrical force down, right? And then you start to notice gravity. In fact, if you could take 1% of the electrons off of you and 1% of the electrons off the Earth, you would go flying up into space. Okay? Because if you create even a small charge imbalance where you're both the same charge, the electrical force of repulsion you would have would suddenly be way stronger than the force of gravitational attraction. So you really have to do your best to set the stage so that gravity can do its thing and electrical force doesn't get in the way and dominate. Okay? Are there any questions on that? Okay, so think about the very, very special circumstance that you happen to live in where gravity starts to even be noticed, okay? It's a very extreme situation. On the atomic level, gravity doesn't matter at all, okay? All right, so now that I've talked a little bit about that, I want to get into some really nuts and bolts stuff. Well, and we'll have a nominal excuse to include Coulomb's law in a calculation. This is really mostly a review of how to do force combination vector addition from Physics 1. So I want to quickly knock out a couple examples. My first example, I guess this is example 2, because the last one I did was an example as well. This will be a one-dimensional problem. So the kind that you may have liked from Physics 1, where only thing you have to really decide if the two forces are in the same direction or in opposite directions. You either add them or subtract them, that's kind of it, right? They're either working with each other or against each other. There's no more options than that. So let's kind of go through that one first, and then we'll from there we'll expand. So I have three charges, Q1, Q2, and Q3. And let me give you some distances. I'll say this is 0.5 meters. I'll say this is 0.2 meters. If you want, you can take those center to center. Same thing applies, although usually with charges we consider that they're point particles and we don't worry about that too much. Let me give you the amounts here. Q1 is going to be a negative charge. Q2 is going to be a positive charge. And Q3 is going to be a negative charge. And those are the amounts. Now I've expressed them in microcoulombs. So first of all, you want to be on the lookout for that. You want to convert those into coulombs before you plug them in. You want to stay in SI units. And I do want to point out that even though a microcoulomb is relatively small, 10 to the minus 6th, right? That's what micro is. Remember, the elementary charge is 10 to the minus 19th. So even when we're talking about a microcoulomb charge, that's still an imbalance of billions of protons and electrons. Okay? So if something is a minus charge, it means that it has more electrons. If something is plus charge, it means it has more protons. But these are imbalances of large numbers, because the microcoulomb level is way above the floor of the elementary charge, 10 to the minus 19th coulomb. Okay, so what else? I should give you a question I'm going to ask about the scenario. Here's my question. First, I just want to draw in all the forces of interaction. And then I want to identify the net force on, let's just say, Q2. I'm just picking one of the charges for us to analyze. So A is more of a conceptual question, and then B is where we actually get to calculate. So let's start with drawing in all the interactions. To help, I'm going to at least label the sign of the charge here on the diagram, so we don't have to refer back to that other list. So then we can just look at the diagram and draw them in. Let's start with Q1 and Q2. What do they do relative to each other? They attract. So these two are going to attract. And for bookkeeping purposes, I'm going to label them like this. This is F12, this is F21. So if you haven't seen that labeling scheme before, the first subscript is what the force is on. I'll put it over here. What does the force act on? And the second one is where it comes from. So this force, for instance, over here, that's the force on charge 1 from charge 2. This is the force on charge 2 from charge 1. In fact, Newton's third law is that those two forces are equal and opposite. And we might write that like this. And we can compute the size of that attraction with Coulomb's law. If some of you may have seen it with a comma in between, which may be more palatable to you, so on, comma, from. For me, you're never going to have double-digit number of charges, so this is not like the force on charge 12, okay? This is force on charge 1 from charge 2. So there's no reason to have a comma. So that's my first force. Let me do the next one. How about charges 2 and 3? How do they relate to each other? They attract. So We have F23 and F32. Am I done? No. Well, a common misconception is charge 2 somehow blocks the 1 and 3 from talking. You got to include them all. Okay. So how do 1 and 3 relate? They repel. So I have, I guess I ran out of colors, so I'll do this one in black again. This one is going to be F13 and F31. At this point, that's it. Every charge has 2 forces from the other 2 neighbors, right? You can't exert a force on yourself, so each charge should have 2 forces from its 2 neighbors. You can check the subscripts if you want. The first should be the same on any charge. It's of course what charge is being acted upon, and then the second number should be both neighbors, right? Okay, so part A is done. Are there any questions on that before I move forward? Okay, so let's move forward here. I want to do a vector addition. Apparently I'm interested in charge 2, so that's just, I picked that out of the hat. I could have asked about any other ones, but I'm now focused in on what is charge 2 going to feel. So the net force on charge 2 is going to be this vector sum of F23 and F21. So at this point, this is just a reminder of how you handle vector addition. In the case of one-dimensional stuff, basically you just have to decide whether to add them or subtract them. But let's be a little more sophisticated than that. Let's pick the plus x direction to be to the right. That's just my choice. Then any forces that point that way are plus, and any forces that point the other way are minus. So if I do the x direction, F net 2, I'm technically working in the x direction. I have a plus F23 and a minus, let me fill this in, plus F23 and a minus F21. So notice that this is my preference for how I handle it. This is the direction. I put that there in the front. And of course, those directions came from the fact that I considered that like repel and opposites attract, right? So those signs came from that. So I've already got the signs accounted for that. And the only thing I need Coulomb's law for is to fill in the size. So this is the size of this force. This is the size of this force. So it's a really good thing that I stuck in that absolute value sign in my Coulomb's law, because I already have the direction taken care of. I just need to fill in for the amount, okay? So I am considering vectors here. I put the plus and minus signs in myself in the front, and then Coulomb's law just swoops in to take care of the amounts, okay? So let's walk through. I'm not going to bore you with the detailed calculation. I'm going to just kind of sketch it out. So what we're going to get is plus, and then K, Q2, Q3 over R23 squared, and then this one, Q2, Q1 over R21 squared. That's another thing that's nice about those subscripts, is the fact that I don't have to go back and figure out which 2 charges are involved, right? I just read them off the subscript. If this is the force between 2 and 3, it involves charges 2 and 3. All right? Now.
Okay, I had a brief glitch in the recording, so just wanted to fill in the gap here on the audio. So I'm getting the distances between the charges, which of course are always positive. Distance between charges 2 and 3 is 0.2 meters, as was given. Distance between charges 2 and 1 is 0.5 meters, also a given. And not that we need it for the problem, but it'd be good exercise to think about what's the distance between charges 1 and 3, which is not relevant here because we're worried about the net force on 2.
0.7, right? Okay, so before I kind of give away the punchline and just do the answers, we can predict here. This is a tug of war for Q2, right? So there's a force on it to the right, a force on it to the left. So we can predict which one should win. So well, I guess it could be a tie as well, right? It could be that the net force is 0. But in this case, let's take a look at what each of these contestants has going for it. Which one has a larger charge, Q1 or Q3? Q3, it's a larger charge, right? So that's going to make the force larger. How about the distance, right? Which one is going to be a stronger force because of the distance? Q3, it's closer, right? It's also a closer R. So Q3 has 2 things going for it, and Q1 has nothing going for it. Who's going to win? Q3. So we're going to find that the net force is no questions asked, or no doubt about it. The net force here is going to be this way. Okay? And in fact, when you compute these numbers, you should find that the attraction here is going to be about plus 11.25 newtons. And this one, the other contestant, is only 0.72 newtons. Okay, so the clear winner is exactly as we conceptually predicted. If you sum those two up, you'll get plus 0.53, or sorry, 10.53 newtons. That's the net force on charge 2 in the x direction. The plus, of course, is relative to the axis that we we picked at the beginning. So we get a plus, that means to the right. Okay. If we wanted to express it a little bit more generically, maybe somebody else decided to use a different positive direction, we might write it like this. The net force on 2 is a size of 10.53 newtons, and the direction is to the right. So this is the size, and this is the direction in a way that's a little bit more universal, because to the right doesn't have to be positive, that's just what you feel like choosing, right? So that's a little bit of a sense of vector addition in one dimension. For all intents and purposes, we were a little bit fancy with our bookkeeping in that we set a positive direction and then called forces plus or minus, depending on whether they point with or against it. But in essence, in one dimension, you're basically deciding, do the forces add, do they have the same sign, or are they opposite, right? Do they oppose each other, therefore you're having opposite signs? Of course, the real tricky stuff comes in when you start to have 2 dimensions or higher. That's where all your vector addition and SOHCAHTOA really comes in. So let me do a quick outline of that. Are there any questions before I do that? Okay, so let's knock out one of those. Is there a question? No? Okay. So again, this is more a refresher on vector addition than really anything else. Throwing Coulomb's law when I want to know the size of the force. So my third example is going to be 2 dimensions. Let's throw in some. Let's throw in an extra dimension. Let's throw in an extra charge. I'm going to put charge on the square. So Q1, Q2, Q3, Q4. Let me give you the numbers here. Plus 10 microcoulombs, plus 5, plus 6. And let's throw in a negative, -3. I'll give it in microcoulombs for convenience, but remember you want to get them in coulomb before you do much with them. I have to tell you something about how far apart they are because that's going to greatly influence the forces between them. I'm going to say this is on a square of side 3 centimeters. And of course, centimeters, you want to get that to meters as well before you plug anything in. And let me again ask a question, very similar question. Let me draw all the forces on Q2 only. We're going to be here all day if we do all the forces on all the charges. And then let's do that in anticipation of calculating the net force on Q2. All right, so let's go ahead and do that. It's nice and convenient to at least put the signs of the charges in here so we can do our attraction or repulsion just by looking at the diagram. Let's say Q1 and Q2. How do they interact? They repel. So what's the direction of the force on Q2 there? The right. That's F21. I guess I might as well draw the reaction over here, although I'm not going to do anything with it. Let's, I guess, think Q2 and Q4 next. How do they react? They attract. So what's the force on Q2? Downward. That's F24. And might as well draw the other force, the reaction. Not that we're going to do anything with it. We're interested in how Q2 gets pulled by its environment, not how the environment in turn gets affected by Q2. And then finally, how about Q2 and Q3? They repel. They directly repel, and they repel directly, not caring about the fact that you don't like things that are diagonal on the board. Okay? So this is F23 and F32. So what we have here is a bunch of forces which are not necessarily along the same line, and we need to remember how to do vector addition for that. So let me remind you from Physics 1, what do? If the direction of the acceleration is known, then you can pick one of your axes along that. That's your classic trick for an inclined plane. But if the direction of the force is unknown, or the direction of the acceleration is unknown, or possibly 0, then you just pick something for convenience. And you pick something for convenience, so you have to do as little of SOHCAHTOA as you possibly can. So here, I'm going to pick my classic choices, not because I always pick that. Sometimes that's the worst decision you could possibly make. But in this case, that puts 2 out of the 3 forces along the coordinate axes, right? So I don't have to break 2 of the forces into components. It only means I have to break up force 2, 3, right? So that one is going to need SOHCAHTOA. All right? So let's take stock here. We'll do our classic vector addition. F net x, F net onto x direction, F net onto y direction. So first of all, F21 is entirely in the plus x direction. It's nothing going on in the y direction. Okay? The entire force is devoted to the x direction. For F24, which I'll list next, I guess, that's entirely in the minus y direction, so has nothing going on in the x direction. And then, finally, we have F23, which has contributions to both, right? So this is plus as well. So it makes a contribution in the plus x direction and the plus y direction as well. And hopefully you remember how to do SOHCAHTOA. Goes like this, right? So just because I only have 5 minutes left, I want to get through this example. If you don't know how I got those, let's talk about it. Okay, so looking at the x direction, everything is plus direction, so there's no question that this particle is going to be pushed to the right. Okay? This is positive, this is positive. Right? Use Coulomb's law to calculate what the sizes of the forces are. What are the things that might be tricky? What do you use for the theta?
45 degrees.
It's 45 degrees. It happens to be a square, right? So this here is a 45-degree angle, right? And so will this be, right? Because the force is along the line. Questions?
So if that wasn't a perfect square, would we be given that angle?
You could find it if it was a rectangle, right? Let's say this was, these lengths were given, you could use inverse tangent to get this thing, right? So a lot of geometry here to kind of get what you need. It's not necessarily new. Coulomb's law is really the only new thing. So the angle happens to be 45. If it was a rectangle instead, you could get it, or do some kind of geometry to get it. And then, I guess the other thing to mention is, what is R23, right? I'm going to need R23 to compute the force. What is the distance between these two charges? Well, you could use Pythagorean theorem, right? Or it's a 45, 45, 90 triangle, so that's 3 root 2 centimeters. You'd, of course, want to convert that to meters before you did anything with it. Just like you'd want to compute R21, which is just 3 centimeters, you'd want to convert that into meters before plugging in. So I'll leave that to you, and I'll tell you what the answer is, and if you don't get exactly this, we might have rounded off differently. I believe this comes out to be about 500 newtons, and this comes out to be about 108.23 newtons, for a total in the x direction of plus 608.23 newtons. Right? In the y direction, a little bit more unclear, right? We have a downward and an upward pull, and we might be able to figure out which one is going to win. Okay? So let's again take a look at the competitors and figure out which one is going to have a bigger chance. Where do those two come from? The Q4 pulls this thing downward, and Q3, in repelling this thing, partially pushes it upward. So what is Q4? Which one has a bigger charge, Q3 or Q4? Q3, so that has a larger charge. That's one thing, and that may be winning. But which one is closer? Q4, it's closer. So it's not so clear now. The other thing that Q4 has going for it is that all the force is actually acting in the y direction, whereas Q3, of course, is just a component. So here, there's no unambiguous winner conceptually. You just have to compute it and see which one wins. And if you compute this, this comes out to be about minus 150. And this, hopefully not surprisingly, is once again 108.23, because of course, if it's a 45-degree force, then the components in both directions are the same. We find apparently that the downward force dominates, and we have a small residual force left over in the negative y direction. We now have the components of the net force. If we want to find the whole thing, the net force on 2 overall, how do we combine these components? So we just add them? No, right? Pythagorean theorem, right? We have our 2 components, plus 608.23 minus 41.77. We use Pythagorean theorem. That gives you roughly about 610. And then, of course, we don't want to short somebody on all aspects of the vector, so we also find the angle. How do I find that angle? Inverse tangent. So you get about 4 degrees clockwise from the plus x-axis. Okay? So again, for those of you that may not remember, this one's Pythagorean theorem, and this one's inverse tangent. And now we've quantified the influence on charge 2 from its environment. So you'll have some problems like this on your homework where you basically have to review your vector addition and compute problems like this. Okay, so that is it for today.